everybody. That was pretty cool music. Basically, Scala 3 type system is the subject of today's talk, and it is huge subject. So this is just going to be kind of touching at the edges. I have given a few parts of this talk before, but the ending is quite different. So I think now that Scala 3 is released, it's more focused on Scala 3. But basically, what I wanted to talk about is subtyping and what subtyping means. And at the end, I'll kind of talk about opaque types in Scala 3 and how that sort of fits in. So what I'm going to use as an example is these 4 types: fruit, plum, apricot, and pluot. And the way you create types and subtype relationships in Scala is you create a class. A trait is a kind of conceptual class. So when I say trait fruit, I create a type fruit. And if I say trait plum, I create a type plum. When I say extends fruit, that establishes a subtype relationship between plum and fruit, right? So here I've got plum's a subtype of fruit, apricot's a subtype of fruit. And then trait pluot extends plum with apricot. It has 2 supertypes. And what a pluot is it's a hybrid. There's a number of different hybrids they have where they mix plums and apricots. So it has, pluot, that's just a real thing. It has both plum DNA and apricot DNA. And so it is both a plum and an apricot. So anyway, that's my hierarchy. Those are the only 4 types that exist. It makes it a little simpler. Okay, so when I was a C++ programmer, that was the first time I used object-oriented programming. It was C++. And we had something we called, I don't know if we called it an inheritance hierarchy, but it actually had squares with type names in it, and it had arrows between them. But the arrows went down from supertype to subtype. And then later when I switched over to programming in Java, the arrows flipped. We still had inheritance hierarchies, but the arrows are going up, and that was called UML. I mean, they sort of standardized a unified modeling language, and part of that was there was an arrow from subtype to supertype in these inheritance hierarchies. So I kind of thought that was an arbitrary choice until I came to Scala, and I had another insight as to what that arrow means. I mean, it means that it's like, it represents is a subtype of relation. But when you turn it on its side like this, it actually kind of looks like a function arrow. And I think it is a function arrow. I think of it as a function arrow from plum to fruit. So from subtype to supertype. So for example, if I were to write a method that converts plums to fruit, and I call it plum to fruit, and I have a method that takes a fruit, so can eat any fruit, but I have a plum in my hand, I could just convert that plum to fruit by passing it to plum to fruit. I get a fruit back and I pass that to eat, right? But I don't have to, because the Scala compiler will just sort of convert it for me. That's like an implicit conversion. It's not explicit. So that is actually what that arrow in a UML diagram to me kind of intuitively means, is that there is this function that goes from plum to fruit that's applied automatically by the compiler. Okay, so that arrow, when I say implicit conversion, I don't mean Scala's implicit conversion. I mean it converts the types implicitly. So the English sense, it's an implicit conversion. But here's the other thing that I noticed, and I think is significant, is that this kind of subtype to supertype implicit conversion never needs to change memory. You don't need to change anything. I can just have, here's a chunk of memory that's a plum. You know what? I can just treat that as a fruit. I don't change anything. So it's not actually converting it or mutating it or changing it in any way. It's just, I just look at it a different way, look at the same thing. And the other thing about this relation is that it's reflexive and transitive. So what those 2 things mean is, and we never draw this in UML, but there's another arrow on every one of these, which goes back to itself. Because a fruit is a subtype of fruit, because the is a subtype relation is reflexive. Plum is a subtype of plum, and there on the right-hand side, I show apricot is a subtype of apricot, right? And you can think of, well, there is an arrow that goes from apricot to apricot. That's the identity arrow. And if there's a method that takes an apricot, you have an apricot in hand, you can pass it in. That's sort of like that concept. What transitive means, the other arrow that's missing from this diagram, which we don't usually show, is that given that pluot is a subtype of plum, and plum is a subtype of fruit, that means that pluot is a subtype of fruit. That's always going to be true. So that is transitivity. That is two properties of the is a subtype of relation is reflexive and transitive. Okay. So the other thing that I found useful, or like a way that helped intuitively to think about types and subtyping, is that to kind of imagine types as sets of values. And in type theory, they call these members of those sets inhabitants. So I've got 4 examples here. And so the gray oval is a set. That's sort of like a Venn diagram of a set, sort of. And then the colored circles on the inside are inhabitants or values. You can think of them as values at runtime. So unit is what's called in set theory a singleton set. It just has one inhabitant. It has one member. Unit is sort of the canonical singleton set in Scala. It has one member, which we write as either empty parens or empty curly braces. That represents the same thing. And I just drew that as a brown circle there inside that set. It just has one thing in it. By contrast, Boolean has 2 things, true and false. And so like pink is maybe true and blue is false. Those are the only 2 inhabitants of Boolean. And your program may have 1,000 trues in it. When you put them in a set, it's just one true. It only, like if you have a set of Boolean and you put true and false in it, and you put true in 1,000 times, there's just one true in it, right? So to think of it this way, like if you're thinking of sets, you have to have some notion of equality. And the way I think of it is like, what does equals mean at runtime? That's sort of the notion of equality. So there's a set with 1 inhabitant, a set with 2 inhabitants. So then the third one here, traffic light, is an enum that I created. This is an enum in Scala 3. I just say case red, yellow, green. What this gets turned into is a sealed trait, traffic light. And you have case object red extends traffic light, case object yellow extends traffic light, case object green extends traffic light. I'm running out of breath. So in Scala 2, you actually can't even say that in one breath, but Scala 3 allows you to say that very concisely with enum. But that is a type. Traffic light is a type that has 3 inhabitants, red, yellow, and green. And then the last example is the set that corresponds to the type int. It has 2 to the 32 inhabitants, which are integers ranging from min value to max value, inclusive, right? These are just kind of hand-picked examples, but most types are infinite, have an infinite number of inhabitants, like string. Maybe there's a finite, if on the JVM there is some actually maximum string length, I don't know. But if there was, then I guess there is actually a maximum number, a finite number of strings possible, but it's for all practical purposes, infinite, and most types are like that. Anyway, that's I think a useful way to think of it. And when you do think of types as sets of values, then is a subtype of maps to is a subset of. So here, I've got my hierarchy of 4 fruits on the left, and on the right, that's a Venn diagram showing sets and members, right? And you can see that I've got, and this again, it's a contrived example. So I'm going to pretend like there's 1, 2, 3, 4, 5, plain old plums, which are dark purple, and there's 4 plain old apricots, which are kind of bright orange. And in the middle, there's 3 pluots. And pluots are both plums and apricots. So that's like an intersection or a subset. So because pluot is a subtype of plum, over here on the left, that means pluot is a subset of plum, the set on the right, right? That's what it maps to. And if you look at the little symbol we use, like in Scala, it's less than colon. That's the same thing that actually looks a little bit like the subset symbol over there to the right. So anyway, so subtype of is subset of. And then when I was first working on this programming in Scala book, excuse me, Martin objected to my use of the term upcasting to describe this widening from plum to fruit. Like when I call eat and I pass in a plum and it changes the type to fruit. I had heard people call that upcasting because you're casting up the hierarchy. And he objected to that because he wanted the word cast to mean something that's always unsafe. So if you use as instance of in Scala, that's unsafe. And it will always be unsafe. Even if it's like stupid obvious to the compiler that it will not work at runtime, he will just let it blow up at runtime. Casts are always unsafe. So I asked him what he wanted to call it instead, and he said widening the type. I'm like, okay. And I didn't really have much intuition as to what that meant until I started thinking about Venn diagrams and types as sets of values. And so if you look over here, I'm going to take this out of full screen mode just so I can point with my pointer here. This little circle around the plum set, you can think of it as a fence. And inside there's, plums grazing on grass, meandering around inside this fence. That fence encloses all plums. If you change it from plum to fruit, you actually move that fence out, you widen the fence. The fence is now a much larger area, but everything that was inside this, fence before, all the plums are still inside the wider fence. And that's, I think, a good intuition as to what, when you go up the hierarchy, things become more general. As you go down the hierarchy, things become more specific. So that's, these names that we give to types represent a level of abstraction. So fruit is more abstract than plum, which is more abstract than pluot. Excuse me. So that's what, you can kind of see when I widen plum to fruit, it still has all the plums in it, but now it could be an apricot because apricot's in there also, right? Okay, so that's widening the type. And now I'm going to make this more complicated. I'm going to add 2 more types to this simplistic, example. In addition to my 4 fruits, I want a top type any and a bottom type nothing. So this is again in set theory. Type theory. They have top and bottom. What top represents when you map it to set theory is the set of all inhabitants, and that's something that does exist in sets. It can't contain itself, but it can contain all of the inhabitants, right? That are values. So that's why if you could think of like any type is a subtype of any. Oh, sorry, any type. That's a bad use of English, but no matter what type you have in hand, it is a subtype of any, because no matter what set you have in hand, it is a subtype of the set of all. No matter what set you have in hand, it is a subset of the set of everything that contains every inhabitant. So that's sort of intuition for what any is. Any is really all inhabitants. It's a set of all possible inhabitants. Nothing is the dual. It's the opposite. It's the empty set. And so the way that's usually described in math is this little, looks like a Saturn with, a circle with a line through it, a 0 with a line through it, I think it is. So that's, it kind of makes sense. Nothing has no inhabitants. There ain't no instance of nothing. You can't make an instance of nothing. And so it's the canonical empty set. And if you go look in Wikipedia, an empty set is a subset of any other set. So just like that's why nothing is a subtype of any other type. It kind of maps to that. Okay, so now we have 6 types in our running example here. I'm going to add 2 more just to demonstrate one more thing I think is helpful for intuition about subtyping. I'm going to add durians and units. So in the Venn diagram over to the right, like as far away from the apricots and the plums and the pluots I can get them, I put durians, and there's 6 of them. And then I'm going to count these things. So I've got 1, 2, 3, 4, 5 plain old plums plus 3 pluots. That's 8. I've got 4 plain old apricots plus 3 pluots. That's 7. So there's 7 apricots. There's 8 plums. There's 3 pluots, and there's 6 durians. There's 1 unit. So what I'm going to do is in the next slide is I'm going to replace the names of types with the count of inhabitants. And this is why, again, it's very contrived. Most times this is infinite, but it still works out this way. So I'm going to just replace it with numbers. And what that will, to demonstrate that what I want to show is that when you do that, the less than colon, it maps to less than or equals. So because nothing is a subtype of pluot, this one right here at the very bottom, nothing is a subtype of pluot, that means that the number of inhabitants of nothing will be less than or equal to the number of inhabitants of pluot, which means 0 is less than 3. Or because over here, pluot is a subtype of plum, that means that the number of inhabitants of pluot will be less than or equal to the number of inhabitants of plum. So that is 3 is less than or equal to 8. So anyway, that's, I just think, another kind of way to think about how things become more general as you go up and more specific as you go down. And it becomes as general as possible at the top when it is anything. It's like a set of all possible inhabitants. And it can't get any more specific at the bottom when it has nothing. Okay. Alrighty, so that's another intuition. So now I kind of want to get into like changes between Scala 2 and Scala 3 and what kind of advancements was made by Scala 3. So there's three mathematical things you can say about what I just showed you, is that Scala's type hierarchy, this sort of type thing I was, this UML diagram is a pre-order. That's called a pre-order in math. It's also a category in category theory, because a category just has arrows in what they call objects, which I'm going to call atoms, because just so it's not confusing. And our types are the atoms, and the arrows is a subtype of. They need to be reflexive and they need to be transitive, and you have a category, and it is one. So that's another thing we can know about it. And then the third thing is it in Scala 3 is a lattice, but in Scala 2 was not. So I wanted to talk about like how that changed and what a lattice is. So what a lattice is a pre-order where there is, for any two types, a least upper bound, which they call in math a join. And for any two types, there is a greatest lower bound, which they call in math a meet. So the reason I say in math is because in Scala 3, there is a join has been used to mean something slightly different. So I won't call them join anymore. I'll just call it least upper bound. And so one reason that this is important to have a lattice is so that there is always a unique least upper bound. Because Scala uses that when it does type inference. So the little bit of code here at the bottom right-hand corner is an example of where, this is a vowel, and its name is F. And it is initialized with an if expression where the then side has type plum and the else side has type apricot, right? So, so the Scala compiler has to figure out the type of F, and the way it does it is it computes the least upper bound of plum and apricot, essentially. It finds the lowest common supertype. So if you go look over in the hierarchy on the left, the lowest common supertype of plum and apricot is fruit. So in both Scala, well, in Scala 2, it would decide that's a fruit. Let's just put it that way. And so that's why least upper bound matters. And there is a kind of a degenerate case where in Scala 2, it could not compute a least upper bound. There is no least upper bound. So to get it, you need to use type parameters. And I'm going to show like three cases of a type, parameterized types. One that's invariant. This one is invariant. And the other one, the next one will be covariant, and the one after that is contravariant, just so you can kind of see the difference. But like pretend like there's only 6 types. I have just these 6 types, any at the top, nothing at the bottom, and the 4 fruits. That's all I have. And then I add trait show of t. And by just adding that one trait, because it's a type parameter, I create an infinite number of types. Because t can be anything. It's like for all t, show of t. I can put any type in for t. So the first thing I can do, and I'll just point, I'm going to go get a minimize screen again and point to these guys. Here's show of any. I'm taking this type and putting it in for t, and I get a new type, right? That's why this is called a type constructor. Can I construct a type by passing in a type? So then show of fruit is this one, show of plum is this one, show of apricot, show of pluot, show of nothing. Okay, so that's all fine and dandy. I've created 6 new types, but now I've actually just created 6 new types. And I can put those in for t, right? So I can take show of any and put it in there, and now I have a show of any. It's getting smaller and hard to read, right? Show of fruit, show of plum, show of apricot, show of pluot, right? And this just keeps going on. Now I have 6 more types that I can put in. And so it goes on and on and on to infinity. Show of pluot, right? Forever. So because this is invariant though, because it's show of t, not show of plus t or minus t, there is no inheritance relationship between all these show types. So, even though plum is a subtype of fruit, there's no inheritance relationship between show of plum and show of fruit at all. If you look at show of plum, it's the third one over. It's, a supertype of nothing, and it's a subtype of any. Okay, so now let's look at a covariant example. The way you make it covariant is a plus sign. And so I'm going to call this basket. And let's say we erase show. That was a mistake. So we're going to delete that. I've got 6 types, any, fruit, plum, apricot, pluot, and nothing. And I'm going to add one trait, basket of plus t, and I'm going to generate exactly the same pattern of types. There'll be basket of any, basket of fruit, basket of plum, basket of fruit, basket of plum, basket of apricot, right? All the same exact patterns. But because it's covariant, there's now an inheritance relationship between these parameterized types. So whereas before, every one of these, show types was a supertype of nothing and a subtype of any, Now, because, for example, plum, I'm going to point with my pointer here, because plum is a subtype of fruit, that means basket of plum is a subtype of basket of fruit. That's the case. And because basket of plum is a subtype of basket of fruit, that means basket of plum is a subtype of basket of fruit. See? So basically what, this kind of, shape and the colors gets repeated here, and then it gets repeated here, and then throughout all the way to infinity, you keep getting more baskets, and the shape, stays the same, go all the way to it forever. So that's what covariance looks like. And contravariance is always kind of the weird one, but it's really not that weird. It's about what a type can consume. It's about what you can pass into it, which means it's going to eat it. So, hopefully that you can kind of intuit that, like an eater of T, like if a method takes an eater of plum, you can pass an eater of plum in it if you have a type, a value of that type. And the only thing that method can do with that eater of plum that you pass into it is pass plums to it. It can feed it plums, including pluots, because pluots are plums. It can also feed it nothing, because nothing is a subtype of plum. It's fine. And then that's all it can do. So it's actually safe to pass in an eater of fruit where an eater of plum is needed, because an eater of fruit can eat plums. That's the only thing that can be fed to it. And if you can eat any kind of fruit, you can certainly eat plums. So I'm going to point again. And this is the contravariant thing is, because plum is a subtype of fruit, and this is a minus sign, a contravariant type parameter, that means that eater of fruit is a subtype of eater of plum. The arrow is kind of flipped. The direction of the arrow goes different. I wanted the arrows to always go up. So what I did is I flipped the hierarchy. So, you start out with green on top and blue on the bottom. Now you have green on the bottom, eater of any's on the bottom, and eater of nothing's on top. And eater of pluot is on top, and eater of fruit is at the bottom. So it does a similar kind of thing to, that the covariant thing does. This sort of shape gets repeated to infinity, but each time it does it, it flips again. So here, because let's see which one would I use? Because eater of plum is a subtype of eater of pluot, that means that when you add another eater layer, it's going to flip again. That means an eater of pluot is a subtype of eater of plum. It flipped. And you can see this because, like, it starts out green on top, then it's blue, then it's green, then it will be blue, then green, then blue, then green. And down here it starts out blue, then a green, then blue, then green, then blue, then green. So it kind of goes to infinity that way. So anyway, that's actually, hopefully that will, all those colors might give you some intuition onto contravariance, which is what always gives people a lot of trouble. So all that brings me to the problem in Scala 2 with least upper bound. The problem with computing the least upper bound, it's a little bit tricky to actually make it happen. But what, this bit of code here will actually manifest it. I go back to my basket case, and I create two subtypes of basket, fruit basket and int basket, and I use f-bound polymorphism. So what f-bound polymorphism is it's when you use a class that you're defining as a type parameter in the supertype. So like I say, class fruit basket extends basket of fruit basket. That's allowed in Scala, and a place you may have seen it is ordered. When you use ordered, like you're making case class person extends ordered of person. Basically, you're using the person as a type parameter while you're defining class person. So int basket's the same kind of thing. Class int basket extends basket of int basket. And then the problem comes when the Scala needs to infer a type for B down here in the lower left corner, where the then side of this if expression is fruit basket, and the else side is int basket. So it has to find the least upper bound of fruit basket and int basket. So then it looks and says, well, fruit basket is a basket of fruit basket, and int basket is a basket of int basket. So what's the least upper bound of those two things? Well, then you got to go look inside at fruit basket again and say, well, fruit basket is a subtype of basket of fruit basket, and int basket is a subtype of basket of int basket. And basically what you end up with is an infinite series. So if I'm going to close this here, and if you look over here, these are, I mean, one upper bound or one supertype is basket of any, that would work, but it's also a basket of any, which is more specific. So the least upper bound is the lowest one down. So this would be a better candidate than this one, but it's also a basket of any, which is a, another more specific subtype, right? So this goes on to infinity. Basically, the least upper bound is an infinite number of baskets of any. So the way that is solved in Scala 3 is that the addition of union types. And what a union type is a, it's basically between plum and apricot and fruit. In Scala 3, there's another type called plum or apricot with this pipe symbol. And what that maps to is, if you look over on the, the Venn diagram to the right, is a intersection of sets, right? So plum is a set of inhabitants, apricot is a set of inhabitants. Sorry, the union. It's the union of sets. It's called the union type. The union type, plum or apricot, is the union of these inhabitants. So it's all the plums and union all the apricots, which is, in this case, the same as fruit, but it doesn't have to be. I mean, this is a very contrived example. So the way that works is, if in Scala 3, the type of B is just inferred to be fruit basket or int basket. So that solves this problem. And that is defined to be the least upper bound in Scala 3. All right, so that's union types. The dual to that is the intersection type, which is an extra type that's inserted below two types. And that is defined in Scala 3 to be the greatest lower bound. So the greatest lower bound of plum and apricot is plum ampersand apricot. And that represents the intersection. If you go over and look at the Venn diagram to the right, the little boat in the center, I'm going to point to it with my arrow here. This little boat here is the intersection of the plum set and the apricot set, and that's plum intersect apricot. That is the intersection type plum ampersand apricot in Scala 3. It has those three inhabitants, which in this case is the same as pluoid, but doesn't have to be. Okay, so that's union types and intersection types in Scala 3. And then the last thing I wanted to talk about was subtype relationships in refinement types, essentially. And so one of the things I wanted to mention is that, I like this word coercion for when you have to change memory. So I use the example float to double, because there's an implicit conversion in Scala from float to double. And this has to change memory. I can't just look at the float memory as if it's a double. I have to change it somehow. So like, even if I'm on a 64-bit architecture and a float is stored in 64 bits and 32 bits are unused, I have to move it around because the exponents is in a different position, for example. So that I just, that's an implicit conversion, but it's not a subtype widening kind of conversion, because I have to change memory. And then just honorable mention, I don't consider boxing and unboxing, even though memory is kind of changing under the covers, as being violating this can't change the memory thing for subtype to supertype. In Java, you see this. There's a primitive type int which can reside on the stack, and then there's a wrapper type Java lang integer which is on the heap. And when you box, you take something from the stack and you put it on the heap, and when you unbox, you take something on the heap and you put it back on the stack. But in Scala, that's just, int with a capital I, and this is sort of behind the scenes boxing and unboxing, doesn't really change the fact that it's an int. So, okay. So the last thing I wanted to show you is about this any vowels versus opaque types. And let me go over here to this in the Scholastic library is a sister library or a companion library to Scala Test. It's things you can use in your production code that was also useful for testing. And there's a package in there called AnyVals, which we have a bunch of AnyVals, and I'll show you how they're defined. One of them is called posint, and it represents a positive integer. And it just extends AnyVal here. and it's backed by an int. And then we added a bunch of methods, all the methods, you can see them in Scala doc easier probably, all the methods on int, that's the object. Here's the class that, kind of made sense for pos_int. One of the things we didn't add is absolute value because, it will always give back the same thing. So I didn't add that one. You can just say dot value to get that. But there is also a pos_int, for example, that had 0 to it. And then in the companion object, we had a bunch of factory methods, and we have a bunch of implicit conversions that widen these things to different things. So like if you have a pos_int in your hand and you need an int, you can just use the pos_int as an int, and it will use this implicit conversion. And the same thing, there's one to pos_int, widen to pos_int. Positive or zero int, any positive int is going to be a valid positive or zero int, just won't be 0. So we've made an implicit conversion for that one, for example. Okay, so I wanted to demo that real quick. Let's see here. If I import org.scholastic.anyvowels.star, so it's Scala 3, I can say pos_int 42. And that gives you a pos_int. If I say -42, it actually gives you a compiler error. So this apply method that we're calling here is a macro that looks at compile time to make sure this is valid. So it doesn't let you, for example, use a non-literal here. It won't, because it can't prove at compile time that it's valid. So it asks you to use a different construct apply method. There's a bunch of them. From gives you some or none, right? And there's a bunch of others. But once you have one, those implicit conversions allow you to widen them. So I can say pos_int 42 or 3 is, give this, I would like you to widen it to pos_int. This is called a type ascription. And it's like a safe, I shouldn't use the word cast, but it's a safe conversion from one type to another. It will work if this is a supertype of this guy's type, and it will work if there's an implicit conversion from the left side to the right side here. In this case, it's an implicit conversion that we wrote. And then we also wrote one from pos_int to int, right? So that's why you can implicit convert from, you can treat a pos_int as a int. And the other interesting thing is that we actually have a narrowing conversion. You can take an int and narrow it to pos_int if it's valid and it's a literal. So that we actually, it's the same apply method, but it's an implicit conversion. So it's a macro that proves at compile time that it's valid. So it won't let you, convert a negative number. Excuse me. Okay, so that's my demo for any vowels. And I wanted to show a few diagrams to sort of give you an intuition as to that these things are actually conceptually subtypes. So here's looks kind of like a Pac-Man, but it's a Venn diagram for neg_int. It has all the negative integers from -1 down to min value, int.min value. If you add 0, that is the set of inhabitants of neg_z_int, right? And then pos_int similar. Here's all the positive numbers. Starts at 1, goes up to max_int, int.max value, If you add 0, that's pos_int. And if you intersect these, the only thing that they have in common is 0. The only thing in common between pos_int and neg_z_int is 0. And in Scala 2, there was no type to represent that. But in Scala 3, there is, which is you have singleton types for literals like this. And it looks kind of funny. I'll kind of demo it here. I can say val x:0 equals 9. Let me get rid of that. 9 equals 9. If I say that this means that it is a it is an int that has the value 9. That is the specific subtype of int that is the value 9. So if it's 9, I can't put an 8 in there. That won't compile. It says, hey, I found an 8, but I require 9. And so what you'll notice here is the colors are different because this is the type 9, and this is the term 9. This is like the value, the 9 you've been using all along. This is the new 9 in Scala 3. which is the type 9. So there is a type 0, which I can go back here, to represent this now. So I just wanted to mention that. That's in Scala 3 also. Excuse me. And then the union of posient and nexient is int. I mean, it's the same inhabitants. It's all inhabitants of int. So the intersection is, 0 the single time. The union is int. So the thing the last thing I wanted to point out is that the implicit conversions that we created, I mean, that I do think of these as a kind of subtype, because if you map them to sets, they're subsets. And it's transitive and reflexive. So if you have a posy int in your hand, it will be a valid int, like a positive or zero int is either 0 or 1 or 2 or 3. Well, those are valid ints. So that is a kind of subtype of int. It's always safe to convert a posy int to an int. And a posint is safe to convert to a posy int, because a posint won't be 0, but it'll be positive, and that means it's a valid posy int, right? But in our case, because implicit conversions don't stack, they're not transitive, and we had to actually add this conversion ourselves. So I did. There's an, in the posint companion object, there's an implicit conversion from posint to int, which you don't need if it's a subtype. So that brings us to Scala 3's opaque types, and this is the last slide. The difference between opaque types and any vowels is any vowels can not only extend any vowel, but they can mix in universal traits, they're called, which are traits that have abstract methods in them. An opaque type cannot do that. It just sort of like fronts for a backing type. But what the any vowel has to do to use it as an interface is, it's like one of those universal traits, is box it. So there is a boxed form and an unboxed form of every any vowel. And there is no such thing for opaque types. An opaque type is just the backing value. So because I say opaque type posy int equals int, I'm going to skip over the subtype thing there. Whenever I'm using a posy int, it's an int, whatever that means. Whatever that type is what it is exactly at runtime. So it can be more efficient because it avoids boxing compared to any vowels. And you can express subtype relationships. So I can say that my opaque type posy int is a subtype of int right there. I point to it. I put it right here. That's a bound. And then when I made my posint, I can say that's a subtype of posy int. And that actually means it's transitive. So I can demo this guy real quick. Okay. So this is that example. I'm going to import it. Oops, look what I did. I had a Scala 2 accent there for a second. So now this is not scholastic. This is just this code that I've pasted from a slide. I can do the same kind of thing. I can say a posy int 42 is an int. And that is actually using this subtype relationship here. And I can say a posint, if I can get there, because of this subtype relation, I can do the same kind of thing, right? But because it's actually, the compiler is doing this, I get the transitive thing, and the, posint is also an int, and this is the, using the subtype relationship. So the other thing I would say about the difference is that in an any vowel, like I mentioned in our posint in Scholastic, we didn't put the absolute value method on there because I thought, well, there's two ways to say the same thing. Dot value gives you the absolute value. So let's leave that off. When I say it's a subtype of int, I actually inherit all the methods. So I inherit apps, and I can't get rid of it. So that's the other difference between the two. So that is my talk. The only other thing I wanted to mention was that we have done a major overhaul of this book, Programming in Scala, and there's a few more days left before we send it to the printer, and we are welcoming all feedback. So if you wanted to get it and have some time the next few days, this would be a great time to do so, so we can get feedback from you.